Okay, so now we're going to use Green's theorem to find a very nice formula for areas of polygons. Um, so you might recall that the area of D we can write as a double integral over D of 1 dA, and Green's theorem. So Green's theorem here said that the double integral over D of q sub x minus p sub y dA was the integral boundary here, p dx plus q dy, assuming the hypothesis of Green's theorem are satisfied. And so now we do a little trick. If we let p be negative 1/2 y and we let q be 1/2 x, then our q sub x minus p sub y is 1/2 minus negative 1/2 is 1. So our area then, which is just 1 dA, is integral around c negative 1/2 y dx plus 1/2 x dy. Okay? And what we can do now is consider how this works if we have maybe some polygon. And here I have some x1, y1. Here's x2, y2. Here's x3, y3. Here's x4, y sub 4. And this is a 4 here. And I want to go counterclockwise, like so. So if I can compute the line integral along these line segments, I'll call this C1, C2, C3, C4, then I can use that to find my area. So this isn't so bad because I know how to parameterize C1. For C1, I'm going to let x be x1 plus t, x2 minus x1, and I'm going to let y be y1 plus t, y2 minus y1, and t here is going from 0 to 1. And I might also just notice here that dx is going to be x2 minus x1 dt, and dy is going to be y2 minus y1 dt. So now I can put these back up into my expression, and I want to find now, so my integral, okay, so now my integral over c1 of negative 1/2 y dx plus 1/2 x dy is going to be the integral 0 to 1. I have a negative 1/2, and then y1 plus t, y2 minus y1. And then I have x2 minus x1 dt, and then plus 1/2 x1 plus t, x2 minus x1. I have a y2 minus y1 dt. And kind of amazingly, we get lots and lots of cancellation. And this works out to just be 1/2 integral 0 to 1 of x1 y2 minus x2 y1 dt, which is just 1/2 of x1 y2 minus x2 y1. So I have a nice little formula here. So if I think about my integral over my integral over c now of this negative 1/2 y dx plus 1/2 x dy. Well, I'm just doing the thing for all these line segments, right? So I'm going to have a 1/2, and then here I'm going to have a x1 y2 minus x2 y1 plus I have a x2 y3 minus x3 y2 plus then I have a x3 y4 minus x4 y3, and then finally the last one we're going back to the first one. So I have x4 y1 minus x1 y4. Okay? And this is just a fantastic formula because it's so simple. All we're doing is multiplying and subtracting and adding there. And then you can generalize this. You can have all kinds of things here bounded by line segments, and you can find the area of these strange shapes the same way. It's just your last one is going to be x sub n y1 minus x1 y sub n. But you see the pattern here. And so again, very beautiful theorem.